The chain rule. This is about to tremendously expand upon the amount of things that you know how to take the derivative of. You guys are all rookies right now, and you're still going to be rookies after this lesson, but you're going to be less of a rookie after this lesson because you're going to know how to do the derivative of a lot more things. This thing is so important. We're going to be using this chain rule through the entire rest of the year. That's what we're going to call this a mulberry day. Mulberry, I have a mulberry marker in my classroom. This isn't 100% mulberry, but it's the closest thing I can find to it for this video. But in my classroom, I got a mulberry marker, the mulberry marker that signifies importance, all right? It's gotta be very, very important. You know, if you take a mulberry marker to college with you, you gotta use it only for like really important things. So anyways, what we're about to do here, this is the notation for this. All right, so it works when you have composition functions. What you do the derivative of the outside function, leave the inside function alone, times by the derivative of the inside function. You're going to have to do some of that notation stuff, you know, on the AP test and then some of your homework there. But right now, we don't have to worry about that so much. We're just going to go straight to these problems. Here's how powerful this thing is. Like if you're going to square a binomial, you could actually multiply it all out, take the derivative, right? But if you have to raise it to the 80th power, if you have something like this to the 2/3 power, you can't multiply that out, and you're not going to want to multiply that out. So the chain rule concept is going to take care of this derivative for us in a matter of seconds. It's a very, very powerful thing, and you just got to make sure that we practice this. It's going to be easy for everybody eventually. Some of you, this will be easy for you after about 30 seconds and you'll be fine the whole rest of the time. Some of you would just take a couple of assignments to work. We're going to get a couple of assignments over this section typically. Some of you will be fine on the normal ones, but then when we slide down to the trigonometric problems, then some of you will have issues with the trig. So we just got to recognize what kind of problem it is. I'm going to constantly ask you, what is it? Is it a power? Is it a product? Is it a quotient? Is it a trig problem? And then we need to follow the proper pattern right there. So now these first three problems are all powers. This is something raised to a power, something raised to a power, something raised to a power. So we're going to apply your easy power rule where you multiply by the power, decrease the power by 1. But I'm going to keep referring back to this guy right here. If I have something raised to a power, here's the chain where you're going to multiply by the power, leave that inside alone, decrease the power by 1, and then the extra piece when you're doing the chain where you're going to times it by the derivative of that inside part right there. So this is the power pattern. And so I just want to share with you how we're going to apply the chain rule to this and get the same thing as if I were to multiply that out. So if I apply the chain rule, so you're just kind of ignoring what you have inside. You just see something raised to the second power. So when you take the derivative, you're going to multiply by that power. You need to leave the inside alone. I said you don't even see what you see inside of there right now. So you leave the inside alone, decrease that power by 1, and then you keep working your way to the inside. Now you look on the inside, and you see that you have an easy 3x minus 1. You have to times it by the derivative of the inside. So the derivative of 3x minus 1 is 3, and then you have 2 times 3 to get a 6 right there. And notice that these two answers are the same. They are equivalent to each other. But where we can really use that is when we have a raised to the 80th power. So again, when you see something raised to power, I want you to ignore that. You don't even see what that is, all right? That's just like a hooded sweatshirt or something like that, right? You got a hooded sweatshirt raised to the 80th power. So ignore the hooded sweatshirt. You're going to multiply by the power. You're going to leave the sweatshirt alone. It's warm outside. You're going to decrease the power, or it's cold outside, like in the fall weather, bonfire weather, something like that, wear that hooded sweatshirt. But anyways, you're going to multiply by the power, leave the hooded sweatshirt alone, decrease the power by 1, and then you have to always work your way to the inside. Now, when you look inside there, you realize, oh, that's not a hooded sweatshirt. That's a 2x plus 3 binomial mathematical expression. So the derivative of 2x plus 3 is just going to be 2. So you just times it by the derivative of the inside, and then you're okay. So sometimes at the beginning, we forget the times by the derivative of the inside. Sometimes we do stuff a little bit too soon. So we just want to practice this and be perfect with this because the chain rule is extremely important. We're going to be doing this every single day through the entire rest of the year. And then you could just go 80 times 2, make that 160 real quick. There's your first derivative. If you have to do a second derivative, do it again. Multiply by the power, leave the inside alone, decrease the power by 1, times it by 2. So you can do first derivative, second derivative. If I say find the slope of the curve or the slope of the tangent line at x equals 5, plug in x equals 5 right there. Boom, that's going to be the slope of your tangent line. If we ask you for the equation of the tangent line, then you can have a point and a slope and then do your point slope form. All right, so let's do another power. You have something raised to a power, so let's ignore that inside part there, that's just like some basketball shorts or something, or a basketball. Let's do a basketball, right? Raised to the 2/3 power. All right, so you're going to multiply by the 2/3, all right, and then leave that basketball alone. So multiply by the power, leave that basketball alone, decrease that power by 1. So that'd be negative 1/3. And then you have to just times it by the derivative of the inside part. So that'll be 15x squared. All right, and then just simplify that. So you're going to get like what, 30? You got 30 divided by 3, which is going to give us 10x squared. And remember, same rules apply, what we've been doing. Get rid of those negative exponents. You could drop this down to the bottom. Make that a positive 1/3 right there. And then there's your first derivative. All right, so real important to just leave that stuff alone. For whatever reason, when we get to the trig problems, sometimes people forget that, okay? So sometimes they forget to leave this alone and they put that 15x squared right in there and they just have like all of it gelled together. So you gotta make sure you leave that alone. So for example, like when you look at this pattern, notice that, you know, if you pretend that pattern is like you take your dog out for a walk and it like, you know, like doo-doos on the sidewalk, right? And you just got like a pile of dog poo right there, raised to the nth power. You multiply by the power, and then what you do, you literally leave that alone, all right? You leave that dog poo alone, decrease the power by 1, then you take the derivative of the dog poo right there. So make sure you leave that alone, whether it's a normal function, whether it's a trig function, or whatever. I can't stress that enough. All right, now let us go to some trig problems. We already know that the derivative of sine is cosine. And if you need a review of your trig derivatives, you should have this in your notes already. There it is, nice and colorful. Got to make sure we have all those down. And now what we're going to do, if I have the derivative of sine of x, that's going to be cosine of x, right? That's just your answer right there. And now if you have a different angle, watch how easy this is. When you have sine of an angle, what you're going to do, you're going to do the derivative, which is going to be cosine of that angle. Leave that angle alone. But now you have to times it by the derivative of that angle. You're going to times it by 5. And so the 5 is out in front. So you have 5 cosine of 5x. And so what these are, these were powers right here. This was a power. This other one was a power. If I said, what is this? Is this a power? This is a trig function because it's the sine of something right away. And so you go straight to your trig pattern. And this is the other patterns that we're referring to. So if I say, what is it? It's a trig problem. And so if it's the sine of something, right, you're going to go straight to the derivative sine of something. The derivative sine of something is going to be cosine of that thing. Leave that thing alone. And then remember to times it by the derivative of that thing. And so I have just a few listed here. I wasn't going to list all of them. So like, you know that the derivative tangent is secant squared. So if you have the tangent of a blob, you're going to do secant squared of that blob, leave that blob alone, and then you times it by the derivative of that blob. And that blob could be anything. It could be a whole binomial function. It could be a power. It could be a product or a quotient rule in there. And then when you do the derivative of the quotient, you got to do a quotient rule after that. It could be anything that we want it to be, but you just got to recognize what it is at the beginning and then go straight to that. All right, so on this next one, if I say, what is this? This was a trig problem, right? Because you had sine of something right away. If I say, what is this? This is not a trig problem derivative. You have sine of the 3x times the cosine of 3x. That is a product. And if you have a product, you must use the product rule. So you're going to use your product rule. And then when it comes time to do the derivative sine of something like this, then you're going to use your chain rule like we did on this example. So it all kind of merges together. So once you recognize you're multiplying two things together, you can't just do the derivative of each one separately and multiply. You must apply the product rule, and it's very important to recognize that. So you're going to do your, let's say, that product rule together. So you're going to go first function, just write it down, and then you're going to times it by the derivative of that second function. So now you're hitting like the reset. You're pretending like this is your original problem, and you're going to do the derivative and put that right here. So it's exactly like this problem right there. This is a trig problem. If that's my function, I want to do the derivative of that, you got to know your trig derivative. The derivative of cosine is a negative sine, but you're going to go negative sine of that angle, leave that angle alone, and just like right here, we times by the derivative of 5x to get a 5, you got to times it by the derivative of that angle to get a 3 right there. So that's first times the derivative of the second, and then you got to continue your product rule. Sometimes people start the product rule and then they forget to finish it. So now you're going to go plus the second function, just write it down, and now you're going to times it by the derivative of the first. So now you're just pretending that this is your only problem, and you're going to take the derivative of that exactly the way you did this example right there. So the derivative sine of 3x, you're going to do cosine of that 3x, leave that 3x alone, but then you got to times it by the derivative of that angle, times it by 3. Now, if we just simplify this, I have a -3. This is -3 sine squared of 3x plus 3 cosine squared of 3x. And you could just kind of stop right there. If you saw you had like a sine of x and a sine squared of x, you could factor out a sine of x. You know, you could still do GCFs with the variables. If you see those, we're not doing anything with the, I could factor this and play around the double angle formula somehow, but you don't have to. You could just stop right there. So there's a trig problem, there's a product. Right here, if I ask you, what is this? These you got to be careful. I have 3 examples with different trig functions and different powers right there. This is a power. This is a power. This is also a power. Just because you see trig in the problem doesn't mean you're going to go straight to these trig patterns and these trig derivatives. If I saw the tangent of something right away, then I'm going to go straight to the derivative tangent is secant squared, and I'm going to use my trig stuff right there. But see, right here, when at the beginning here, this is what I would strongly suggest you do, is to simply rewrite this as sine of x. You know what that really means? That means you're raising that to the 3rd power. Rewrite this as cosine of 4x. That whole entire thing is being raised to the 3 power, all right? And then this one here, I'm going to rewrite as secant of 7x. Raise that whole thing to the 4th power. Now, eventually, you'll do so many of these, you might not need to do this. Sometimes when I'm making an answer key for a test, something like that, I might just do that just to be extra cautious so I don't mess anything up. But especially at the beginning, because a lot of people who don't do that, they end up putting this 15x squared inside there, and they forget to leave that dog doo-doo alone, right? So you got to just be careful with this, right? Now, what I'm thinking here, this is a power. This is something raised to a power. And so the pattern that we're using is this very first pattern. I don't care what's inside there. If it's something raised to a power, I'm going to multiply by the power, leave that inside alone, decrease power by 1. Then I'll concern myself with the inside, and I'll do the derivative of the inside piece right there. So I'm really the very first step. The approach, the first couple steps on all these problems is the most important thing right there. Because if you're getting started off right, you're going to have all the major stuff down, and you're just going to, you know, like worst case scenario, you might miss a little sign mistake or forget the little thing at the end or something like that. But if you're not getting started off properly, recognizing what it is at the beginning, then that's where you can't get any partial credit, and then it just kind of crushes people there. So I'm going to approach these the same exact way at the beginning that I approach this. Instead of when I go to the inside, it won't be an easy 2x plus 3. I won't put a 2 right there. I'll have a trig function on the inside, and I'll extend that, all right? So let's do this first one. So when I do this derivative, I have something raised to a power. So I'm going to multiply by the power. I'm going to leave that inside alone. Don't even care what that is at that point. I'm going to decrease that power by 1. Then we're going to times it by the derivative of the inside part. Now when I look inside of there, now I care about what it is. So I'm just pretending that that's my only problem now. And you're going to times it by the derivative of that. So the derivative of sine of x is just the cosine of x. And so here we're going to get 3 sine squared x cosine of x. Real quick before I forget, sometimes I get the question, how do you know whether you're going to use the chain rule or not? Here's the thing. This chain rule is so powerful, you could always use the chain rule. It will always work. Technically, you're always using it. You're not even thinking about it. So like go back to this problem here, right? You didn't think I was using the chain rule on that, but technically I was, because think about it. If you apply the chain rule here, the derivative of sine of an angle is going to be cosine of the angle, leave that angle alone, and then you times it by the derivative of that angle. But see, the derivative of x is just 1. So it didn't matter that I applied that chain rule to it or not, because you're going to get the same exact thing. But see, if I did, there's no harm to that. I just went ahead and did that. So same thing right here. Technically, I'm timesing it by the derivative of that angle, which is just 1. So it's like you could always apply the chain rule, just sometimes it's necessary because you have a different number, but the derivative of that is just 1. Then you could either put that in there or just leave that off. It's going to be the same thing right there. So technically, you're always using the chain rule. Just if it's just a single x right there, you don't have to worry about it as much. All right, so same thing here. I see that cubed. I'm going to have this whole thing raised to that power right there. So when I do the derivative, Let's use this dy dx notation. There's our first derivative, right? So I don't care what this is at this point, all right? This is just a this is just a graphing calculator, raised to the third power right here. So if I have a graphing calculator raised to the third power, we're going to multiply by that power. You're going to leave the graphing calculator alone. Who cares about it? Just leave it alone. Leave it in your book bag there. Decrease that power by 1. And then you're going to times it by the derivative of that inside part. Now, when you look inside there, you realize that's not a graphing calculator inside your book bag. That's a cosine of 4x. And so you need to times this by the derivative. Just keep the string going. It's a nice big chain. That's why it's called the chain rule. You need to just pretend that this is your original problem, and you're going to do the derivative of that and write that right here. You're going to do the derivative of this the same exact way as we did the derivative of this problem right here, because this is a trig problem. So if you have cosine of an angle, we're working with this pattern here. If I have cosine of an angle, I'm going to do negative sine of that angle, leave that angle alone, times it by the derivative of that angle. So if you wanted to, you could take your initial trig list and you could kind of replace those with like parentheses right there and add on the derivative of that parentheses like I started to do here. You could do that with all of them and have that one big thing there and study those. But let's just keep on going here. So I multiply by the power, decrease, left the inside alone, decrease power by 1, and now we're going to times by the derivative of the inside. So I know the derivative of cosine is a negative sine of that angle. Leave that angle alone, and then you got to keep working your way to the very inside part. So I need to times it by the derivative of that angle. The derivative of that 4x is going to be a 4, and then we can simplify that. You got 3 times negative 1 times 4, so it's going to be negative 12, and then we get a cosine squared of 4x sine of 4x. This will be simple for everybody. You gotta work at it though. Some of you probably think it's easy right now. Some of you might think it makes sense. And then when you go do the homework, you might have some questions there. So ask those and just keep working at that. But this will be easy for everybody. If it's not, you gotta keep working at to get it to the point where it's just automatic. And then it's very helpful. Sometimes people aren't automatic and sharp with their trig knowledge there. So you can't do these problems. You're not gonna be able to do any of the integrals either if you don't know those trig derivatives right there. All right, so just another power, just since I got time to do these notes here, I'm not like running out of time with the bell or nothing. I just threw an extra example in here. So you got secant to the 4th of 7x. So I would rewrite that like that. It's something raised to a power. So we don't even care what this is. It's just like a baseball hat right there, right? So you got baseball hat raised to the 4th power. So when you do the derivative, you're gonna multiply by the power. You're gonna leave that baseball hat alone. Who cares what that is at this point? You're going to decrease that power by 1, and then you're going to times it by the derivative of that inside part. And so you realize, hey, it's not a baseball hat, that's a secant function. And so you remember the derivative of secant is secant tangent. So when you do the chain rule here, so when you do the derivative of secant, you're going to do secant of that angle, tangent of that angle. Always leave those angles alone. Leave that alone. And then you're going to times it by the derivative of that angle. So then you're going to times that by 7. So you should always have the angles attached. Sometimes people just put secant tangent and they mess up that 7x right there. Secant of that angle, tangent of the angle, leave the angle alone, and then you times it by the derivative of that angle right there. So then I got a 4 times 7, I can make this a 28. You got secant to the third times secant to the first. So that's going to be secant to the 4th of 7x times tangent of 7x. And there's our derivative. So it's really, to me, it gets just kind of fun. And you just, you got to recognize those patterns. Sometimes we'll put more challenging things for that angle. I could put, instead of a 7x right there, you know what I could do? I could put like a quotient right there and make you do the quotient rule at the end. Instead of the derivative of 7x to get to 7, I can make you do a whole quotient rule at the end. So I can make those as easy or as hard as I want those to be. All right, here's our last problem. And this is just a little shortcut that I'm going to share with you here. Technically, you have a fraction, you have a quotient, so you can use the quotient rule. But notice that this is the only time I use this shortcut is if I have a constant on the top. If I have negative 7x on the top, I'm telling you, you're going to be better off just doing your quotient rule. Don't do this thing I'm about to show you unless you have a constant on the top. If you do the thing I'm about to show you when you got variables on the top, if it's not just a constant, it almost always makes that work worse with the simplifying, with the quotient rule, with the simplifying stuff there. So I'm sorry, if you bring it up and try to do a proctor, it almost always makes it worse because you're introducing more negative exponents, especially if you got the fractions. It just gets crazy sometimes there. You're almost always better off Just if you don't have a constant, just do a straight up, straightforward quotient rule. Don't be afraid of that quotient rule and develop some good habits there, because that's where I see people mess up sometimes. All right, but if you have a constant, instead of doing a quotient rule here, look what we can do. I can rewrite this. I'm going to take this guy and I'm going to move it up to the top. And I'm going to need to change that exponent to a -2. See, that's equivalent to the original problem. And now I'm going to do the derivative. But see, now if I have an x right there, then I got to do a product rule. And I just made that problem worse, because then you got the negative exponents in there instead of the positive exponents. So I would just do the quotient rule. So if you find yourself moving up through the product rule, I would strongly suggest against that. Just do the quotient. But if you have a constant, move it up to the top. And now this is just your easy power rule, where you have something raised to a power. So when we do the derivative, you're just going to multiply by the power. So -2 times -7 is a +14. Multiply by the power. Leave that inside part alone. Decrease that power by 1. And then you got to remember to work your way to the inside. Times by the derivative of 2x minus 3, which is a 2. And then so you're going to get 28. And then we should still get rid of the negative exponents. Make that positive. There's our first derivative. So practice that chain rule. Really important that we get that down. Make sure we got the approach down. And when you're studying for an assessment, make sure you're studying the beginnings of those problems. Get the approach down, what you're going to recognize right away. And in case you need to see that again, just you're constantly ask yourself, what is it? Is it a power, product, quotient, or trig? Later on, we're going to do the same thing, but we're going to just add more things to your list. You know, we're going to have logarithms and a bunch of other stuff there. All right. So good luck with that. That's our chain rule. That's our first Mulberry Day of the year, one of the most important sections of the year. We'll have a few Mulberry Days as we go forward there. But when we see that color, when we see that Mulberry marker, that's going to be something real, real important for us. Thank you.